page 78, domain of a function. We actually have talked a little bit about domain in the prerequisite chapter, but here's where we get our official information about domain. So on page 78, it says the domain of a function is the set of all values of the independent variable for which the function is defined. Now, I know a lot of us, when we think of domain, we just think X value. But we talked previously about the fact that you're not always going to have an X and a Y in the scenario that you're working with. And so we need to get to the point that we can look at the example that they give us and figure out which is the dependent variable and which is the independent variable. So the example that we had used was the population over, maybe 10 years in Savannah or something like that. And if we're trying to figure out, we have population and we have time, we're trying to figure out, does the population of Savannah depend on what year it is, or does the year depend on the population? And we said, we don't get to set the calendar. We can't, go change time. So the population is going to have to depend on the year. So the population would be the dependent variable, and the year would be the independent variable. So when we're looking for domain, then, we're looking for the values that are associated with that independent variable. And yes, if it's X, fantastic, but it won't always be an X value. We also said that domain is the input value. It's like what you're plugging in, and then that puts out an answer, and that output is your dependent variable or your range. We also talked about if you had a graph instead of maybe an equation or a scenario that you were looking at. If you were looking at the graph, then the independent variable was graphed on the horizontal axis, and the dependent variable was graphed on the vertical axis. So that would be another way to recognize it. So when we're looking for domain, the domain of a function is the set of all the values of the independent variable for which the function is defined. Now, when we're working in this textbook, it says the domain of a function can be described explicitly, or it can be implied by an expression used to define the function. So in our textbook, when they talk about domain, this is what they're implying. The implied domain for our function is going to be the set of all real numbers for which the expression is defined. So there are two key parts of that definition. The implied domain is the set of all real numbers for which the expression is defined. Okay? So our domain is going to be all real numbers unless we run into two problems. If our function has to have real numbers, what's not real? What's not real? Imaginary, yes. And if we have to have defined values, what's not defined? Undefined, right. So our domain is going to be all real numbers unless we run into two problems. Either imaginary numbers or undefined values. So how do we get imaginary numbers?
Divide by square root of negative.
Square root of a negative number. And how do we get undefined?
Divide by 0.
Division by 0. So that leads us to our domain. Our domain is going to be all real numbers unless we have division by 0, because that's undefined, or we have a negative under a square root or a fourth root or something like that, because that's imaginary. Now you can take the cube root of a negative number. You just can't take an even indexed radical of a negative number, right? What do we mean by even index number? When you're looking at a radical, like down here, we've got this radical, the little number that's right here is your index. If there's no number there, we assume it's a square, so that would be a 2. Or if that number was a 4, so that you had a fourth root or something like that, then that's when we run the risk of picking up an imaginary number. Cube root, perfectly fine, but square root or fourth root of a negative number, we're going to have a problem. So your domain will be all real numbers unless you have a 0 in the denominator, or you have a negative under a square root or a fourth root, or something along those lines. All right, so when we look at example 5, they're going to go through and give us a variety of scenarios where they ask us to find the domain. So for A, they just give me a list of ordered pairs. So in those ordered pairs, what is my domain? The x values, right. And so I could go through and say my domain is just the -3, the -1, the 0, the 2, and the 4. All right, look at B. For B, they give me a function, and we know that this is going to graph as a parabola, but they give me a function and they say, what's the domain? We said your domain would be all real numbers unless one of two things happened. You got 0 in the denominator, or you got a negative under like a square root or a fourth root. Is there any chance of getting 0 in the denominator for this one? Do you even have a denominator? No, so there's no way you're going to get 0 in the denominator, right? Is there any chance of getting a negative under the square root or fourth root for this one?
Maybe.
For B, do you even have a square root or a fourth root? No. So my domain is all real numbers unless I have a 0 in the denominator or a negative under a square root or a fourth root. I don't even have a denominator or a square root or fourth root. There's nothing to have to watch out for then, nothing to have to exclude, so my domain is all real numbers. Now, you literally can write that out in words, all real numbers, or this is the symbol that we use for all real numbers, kind of looks like a capital R with 2 lines. And if they wanted an interval notation, we could give that as well. That'd be the negative infinity to positive infinity. All right, look at C. For C, we have 1 over x plus 5. Your domain is going to be all real numbers unless you get 0 in the denominator. Any chance of that?
Yes.
Yes, because I do have a denominator this time, right? I can't get a negative under a radical, but I don't have a radical. I'm not going to have to worry about that here, right? So let's go back to that. I can't have 0 in the denominator. So here's all I need to do. All I need to do is say my denominator, which was x plus 5, can't equal 0, and then I can solve that. So my denominator, x plus 5, can't equal 0. So if I solve that for x, I would just subtract 5 from both sides, and that would tell me x can't equal -5. So every other value is perfectly fine. I just can't have -5. So you could write that out as all real numbers except for -5. Or if they wanted interval notation, we would say, okay, we start at negative infinity and we go till we get to -5. And then we have to pick up and jump over the -5, and then we can resume on the other side and go to positive infinity. So all real numbers except for -5, or there's our interval notation for it as well. Skip D for just a second and let's go down to E. For E, we have k of x is equal to the square root of 4 minus 3x. Our domain is going to be all real numbers unless we have 0 in the denominator. Any chance of that? No. Or a negative under a square root or a fourth root. Any chance of that?
Yes.
Yes. I do have a radical here, and so I cannot have a negative under that radical. If what's under that radical can't be negative, what can it be? It can't be negative. What can it be?
Positive.
Positive or?
Neither.
Or 0. So every single time we have a square root or a fourth root, we're going to do the same thing every single time. We're going to take what's underneath that radical and we're going to make it greater than or equal to 0. What's under that radical can't be negative. It can be positive or it can be 0. So we will always, if it's a square root or a fourth root or an even indexed radical, we will always take what's underneath that radical and set it greater than or equal to 0. Now, that's a linear inequality. We solved those back in our prerequisite chapter, so we know how to solve that. What do you want to do?
Subtract 4.
Yeah, we could either subtract the 4 or add the 3x. Either one of those is fine, whichever way you want to go. I added 3x to both sides. And then divide by 3, and that is my domain. If we wanted it in interval notation, we could give that as well. So your domain will be all real numbers unless you get 0 in the denominator or a negative under the square root. If you have a denominator, you're going to set the denominator not equal to 0 and solve, and that will be what you have to exclude from your domain. Anywhere that denominator equals 0, you'll have to exclude that from your domain. If you have a square root or a fourth root, you'll take what's underneath the radical and set it greater than or equal to 0, and then solve that inequality, whether it's a linear inequality or polynomial inequality or whatever it is. We know how to solve those. We'll take what's underneath the square root or the fourth root and make it greater than or equal to 0, and then solve that. Okay, now we skipped D because there's really like a little asterisk that we need to add here to this thing we've been saying about your domain's going to be all real numbers unless you have one of these two things. There are situations when you're working in a real world setting, or maybe you're working with a word problem, where there are restrictions on the problem itself that will restrict your domain. And D is a good example of that, because D is the volume of a sphere. Okay, so we have the volume of a sphere, V is equal to 4/3 pi r cubed. When I'm looking at that, first off, I got to figure out what I'm even trying to find the domain of. I know I'm supposed to find domain goes with independent variable goes with X, but I don't have an X here. I have a V and an R, right? Well, remember that we would normally write our equation something like y is equal to 4/3 pi x to the third, so that gives us a little bit of a clue. But you can also see that I would be putting in values for R, and those would be creating values for V. So the input would be R, the output would be V. The volume is going to depend on how long your radius is. So the radius would be independent, the volume would be dependent. So whichever one of those keywords that you're looking for, the independent variable, the input value, the thing that's in the place of X, all of those things tell us that when we're looking for domain, we're looking for the values for R. What does R stand for? The radius. A radius is a distance, right? So what restrictions are there on a distance? It can't be infinite, okay? What else?
Can't be negative.
It can't be negative. So I'm going to have to say that my radius can't be negative. It could be 0. In that case, my volume is 0. And it could be a positive value. So I'm going to say that my radius needs to be greater than or equal to 0. It can't be negative. Now, there probably is going to be some restriction on the other end of it, like you're saying, that it can't be, an infinite value that goes on without end. We just don't know for this setting what that restriction might be. So we won't have a restriction on the other end of it, but typically you're right. You're going to have some type of, you're using a certain amount of material to construct something, and so you do have a limit on what that radius can be. All right, over on page 79, they give us some applications. So example 6 says, you work in the marketing department of a soft drink company and are experimenting with a new soft drink can that is slightly narrower and taller than a standard can. For your experimental can, the ratio of the height to the radius is 4, as shown in figure 1.3. Express the volume of the can as a function of the radius. Okay, so to begin with, they tell me that the ratio of the height to the radius is 4. Okay, ratio is just a fraction, so the ratio of the height to the radius is always means equals 4. Now, that's just an equation, so I can turn that equation around any way that I want to. Like, I could go through and multiply both sides of that by r, right? So if I took this little equation and I multiplied both sides of it by r, I would get h is equal to 4r. If I took that equation and I divided both sides of that by 4, I would get r is equal to h over 4. So I can take that equation and I can, manipulate it in various ways. I can solve for h, I can solve for r, whatever I need to do. It would be the same thing as like distance equals rate times time. If you need to solve for rate, you divide both sides by time. If you need to solve for time, you divide both sides by rate. You can manipulate that equation to be what you need it to be. So for this one, we've got volume is equal to pi r squared h. And they've given me this ratio of the height to the radius being 4, and we've also turned that around and written it in several different ways. So for the first part of this, it says express the volume of the can as a function of the radius r. Now, when they say they want me to write the volume as a function of the radius, what that means is they want me to rewrite that equation for volume, and the only variable they want me to use is radius. If it had said express the volume as a function of the radius and the height, that's what we've got right here. We've got the volume written in terms of the radius and the height. But when they say express the volume as a function of the radius, that means that's the only variable they want me to use. So if I'm only going to use r for this equation, what do I need to get rid of? H, yes. So I'm going to replace h with what it's equal to. So I can come over here and look at the various forms of that same equation that we turned around, and I would want to use the one that tells me what h is equal to. H is equal to 4r. So let's replace h with what it's equal to. So in the place of h, we'll just put 4r. So we could do a little bit of simplifying. R squared times r is going to give us r cubed, and typically we would pull the constant 4 out in front. So sure enough, we've rewritten that volume formula so that the only variable in it is r. So we've expressed the volume of the can as a function of the radius r. For the B part, it says express the volume of the can as a function of the height h. So that means they want me to write the volume using only h. So if I go back to the equation pi r squared h, what do I have to get rid of this time? Yes. So I'm going to rewrite pi r squared h. If I'm only allowed to express it in terms of h, that means I need to get rid of r. So this time let's replace r with what it's equal to. So out of our combinations over here, we found out that r was h over 4. So let's just replace r with h over 4. So pi r squared h. Do a little bit of simplifying. So we had h over 4 squared, that's h squared over 16. So h squared times h gave us h cubed over the 16, and then we had that pi out in front as well. So we've rewritten that volume using only the variable h. So we've rewritten the volume as a function of the height. All right, look at another application. Example 7. It says a baseball is hit at a point 3 feet above ground at a velocity of 100 feet per second and an angle of 45 degrees. The path of the baseball is given by this function. And so here's our function, f of x is equal to, there's our whole function. So if you think about it, we're standing here at the starting point. In baseball, what would that starting point be? Home plate. So we're standing here, the origin is home plate. He hits the ball and it follows this trajectory, kind of like a inverted parabola there, or a parabola opening down. All right. What is your horizontal axis representing?
How far it traveled?
Yeah, the distance that it is away from home plate, how far it traveled, right? And what is your vertical axis representing over here?
Its highest point.
The height of the ball, right, at any point, and yes, it would also show us its highest point as well. So this is my distance away from home plate. This is the height of the ball as it travels, okay? So if I go back to the problem, it says, will the baseball clear a 10-foot fence located 300 feet from home plate? Now, what did you tell me was the distance away from home plate, x or y? X. So it says it's located 300 feet from home plate. So I got to put 300 in for x, right? So again, I don't have a clear-cut maybe domain and range or x and y until I stop and think about what do these values represent on the graph. We said that anything graphed on the horizontal axis would be our domain, would be our independent variable, would be our x value. Anything graphed on the vertical axis would be our dependent variable, would be our range, our output, like our y value, okay? So we can go through and say, since they want to know the height when I'm 300 feet away from home plate, and my x value was representing the distance away from home plate. Let's put 300 in for x. So we'll go through and we'll put 300 in for x and 300 in for x. Absolutely going to throw that into my calculator. There's no need to work that out by hand. And I find out that when x is 300, y is 15. What is that 15?
The height.
The height of the ball. Is that my answer? No, you got to be careful with a word problem that you answer the question that was asked. It didn't say how high is the ball when it's 300 feet away from home plate. It said, will it clear a 10-foot fence that's 300 feet away from home plate? So if my ball is 15 feet off the ground, is it going to clear the 10-foot fence? Yes, and so that's my answer as opposed to 15 feet or something else. So yes, it's going to clear that fence. All right, look at page 80. On page 80 and 81, examples 9 and 10, they give us something called a difference quotient. And you'll notice there's a little icon with each of those examples, just kind of a little funky little thing. That icon, every time we see it in the book, represents an application from calculus. A difference quotient is actually the foundation of a derivative, which is what Calculus 1 is all about. So it's extremely important for what we do in calculus, and thus why we see it in pre-calculus. It's called a difference quotient because you'll notice you're going to find the difference between two things, and then you're going to divide by something, and the answer to a division problem is a quotient. So that's where it gets its name. They're going to give me a pattern to follow. Like in example 9, it says find f of x plus h minus f of x divided by h. Over on example 10, same thing. Find f of x plus h minus f of x divided by h. Sometimes it'll be a little bit different. Sometimes it might say find f of 2 plus h minus f of 2 divided by h. So you just follow whatever pattern that they ask you to find. Okay? So for this one, they told me if f of x is equal to negative 2x plus 4, find this difference quotient. Now, we worked with function notation previously, where we said if they gave me something like f of x is equal to negative 2x plus 4. When they asked me to find f of 2, that means put 2 in the place of x. So we were coming over here and just putting 2 in the place of that x. They asked me to find f of t, I put t in the place of that x. They asked me to find f of 2 plus x, I put 2 plus x in the place of that x. We said if they asked you to find f of smiley face, you would put smiley face in the place of that x. So when they say find f of x plus h, that just means put x plus h in the place of that x. So that's exactly what we're going to do here. When they say find f of x plus h, we're just going to put x plus h in the place of x in that function. So we'll put x plus h in the place of x in that function. So if I distribute my 2, negative 2 times x is negative 2x, and negative 2 times h is negative 2h, and then we still have the plus 4. So there's f of x plus h. So according to the formula, they said find f of x plus h. Okay, we did that. That's what we had in red right here. Negative 2x minus 2h plus 4. Then it says subtract from that f of x. F of x was just my original function, right? If I come back over here, f of x was negative 2x plus 4. So I'm just going to subtract that original function, negative 2x plus 4. And then it says divide the whole thing by h. Okay, divide it by h. So one more time, we're just following the pattern, f of x plus h, that's what we got in red right over here, minus f of x, that was my original function in black right over there, divide that by h. Okay, divide that by h. So we've got it set up. Now we're just going to simplify. So if you have a negative in front of parentheses, remember it gets distributed through the parentheses. So that would give me minus a negative, so plus 2x, and then minus 4. The negative 2x and the positive 2x will drop out, and the positive 4 and the negative 4 will drop out, so that would just leave me the negative 2h in the numerator and the h in the denominator. The h's top and bottom would drop out, and that would just leave me negative 2. So that's a difference quotient. We'll do a couple of them here, and then it will come back up probably 5 or 6 times during the course of the year because they just want to make sure we remember that skill because we'll need it almost immediately in calculus. Okay? All right, so here is our homework for tonight on pages 84 to 86. We're doing 45 through 73 every other odd, 80, 81, 87, challenge 97.